Good morning. Hello, everyone. This is Amr Muhammad, and this is CE432 Traffic Engineering. This is class number 3, or presentation number 3. In this class, we're going to discuss, or just do a very fast review of some statistics or statistical application in traffic engineering. So let's go ahead and start. So, traffic data, and in traffic engineering, we collect lots and lots and lots of data. So we analyze large amounts of data. For example, when we collect some volumes, traffic speed, we want to know what to collect, how to collect, when to collect data. So this statistical analysis will answer some questions that we'll use throughout this course about how much data you need, when to collect it, how to collect it as well. So we do a lot of observe and measure characteristics to some samples or finite samples of vehicles of the whole population. Here it comes two things. Number one, sample, and it's how much time you're gonna take to do the counts on the road and figure out how much data you wanna get from the road. It's definitely gonna be a sample because we have traffic 24/7 on the roads. And another word is the word population, which is the total number of vehicles you have on the road. And to note something is that some of the traffic counts that you can see on the road, they're permanent, like the loop detectors and cameras, and they do the counts 24/7. But sometimes we have a study like we do here in our class, and this study will include that we need to figure out a sample of the whole population of traffic, and we need to figure out, okay, how much time I'm gonna spend there, how much time I'm gonna put, for example, if we're gonna put our own camera or send some people who will do counts, will they spend the whole day or 1 hour, 2 hours, how much time, because it will equal to funds or money, because all traffic projects need some money. So here population is in fact infinite, and we will have some finite sample of vehicles. So we want to answer these questions here. How many samples are required? How much time you need? What is the confidence you have this estimate? So we're going to go ahead and say, you know what, I want to know the speed of the cars. So I'm going to stay there for 2 hours. How confident I am that the numbers I'm going to get will be representative of the whole population. Is it different in the morning, in the afternoon, in the overnight time? So we need to answer all these questions. And also, once we collect the data, we want to model that. So when we model it, we try to figure out a numerical and a statistical model. We call it a distribution that will best describe the observed data mathematically. And another really important thing we do in statistics, let's say that we built something, we added a traffic signal to reduce the speeds, or we just added a hump to reduce the speed. So we want to figure out, did it do a significant, and the word significant is very important in statistics, change in the characteristics of population? When we added this sign, or when we added this kind of pavement, or when we added this signal, did it change the structure, or did it change the environment of speeds and so on? And later on it will be also affecting, for example, safety. And I have tons of examples that I will describe when it comes. So we have two types of statistics. We have what we call here descriptive statistics, and it includes the following. We discussed this very fast in class last Friday. It includes collecting, organizing, summarizing, and presenting data. It has no conclusion here, so you're just representing your data. Okay, so for example, for your marks, let's have an example here in class. When we calculate your average marks, how your marks are above and below the average, we can create some table with data, some charts, some pie charts, some regular charts, frequency distribution that will tell me, yeah, this is the data for this class. Also in traffic engineering, when we want to represent, for example, an interstate, we collect the data and we give our clients, usually the government, or we give the students, or we give the people, we say, yeah, the average volume of this road is this number, the average volume of speeds is this number. So this is called descriptive statistics. Or we make some inferences, and that's the second type of statistics. When we do hypotheses, we do some testing, we determine some relationships, and we do also some predictions. So here we try to not only represent the data, we want to make some conclusions on this data, and sometimes we do some changes as well. So for example, if you represent tech, you want to estimate and test value hypothesis about your average grade in the school. What is the error of that? and the probability of error if we are inferring. Also, when we get back to the traffic engineering, let's imagine that we want to build a bridge, or we want to put a traffic signal, and we want to figure out is it good or bad. So we make some kind of hypothesis and we test that. This is called inferential statistics. We're going to do a little bit of both, but we're going to be focusing more on the easy one, the first one, descriptive statistics, and also we're going to figure out some of the distributions as well. Most of the inferential statistics will be left for your graduate studies in case you wanted to continue working some graduate studies in traffic engineering. You're going to be having some really strong background in statistics. It's not, by the way, it's not so hard, it's easy. All you have to understand is how to use it, and the beauty about statistics here is very practical. You're going to be using these tough statistical equations in some kind of a traffic engineering data, so you're going to feel how beautiful it is to work with it, and it's very powerful. It's a very powerful tool. So this is how it works. You have the data. You can go up here. You can let me just go ahead and use my pen. So here, where is my pointer? Here. So this is your data. You collect the data. I'm going to talk about data a lot in this class. You can go this way. So you can either have descriptive statistics, or you have, and here you have summary of the findings of the study. You just give some summary of what's going on actually in the real life. Or you can go down. Once you do this, actually sometimes you do both. And this is the inferential statistics, where you do some kind of generalization and come up with some results of conclusions and tests and so on. So we have now, let's go ahead and go into the statistical analysis. So we have two types of statistics. We have something called discrete and something called continuous. It's very simple. And when we talk about now statistics, we're gonna define something called a variable. A variable is very easy. Anything you study. Speed is a variable, volume is a variable, your height is a variable, your length is a variable. Whatever you do, your weight is a variable. So we're testing something that is random, something that's different from one place to another, from one lane to another, from one road to another, from one person to another. We call it a variable. It's different from one to another. So here can take any value between two specified values. We call it continuous. So let's say we're talking about heights. Height is continuous. Why? Because you can have any number with any fraction. You can have as much fractions and much numbers after the decimal point. This is called continuous. So when we have here, like you can see here, this ruler, this is continuous. So you can have any number between 1 and 6, 0 and 6. Any number, we call this continuous. So it's the variable that it's easy, it's continuous. It can take any number. This is a little bit hard in predicting, because a probability of having going to my class and I have exactly a person of height 5 and 4396, it's gonna be 0, because we cannot have this exact number with the decimal point. So some of the examples here: height of children, weight of cars, speeds. When we talk here speeds with a decimal point, time to wake up in the morning. So we don't wake up in the same exact minute every single morning, or same exact second. We have a different second every morning. So here, speed of a train. So when we do some analysis on this, we use something called, which we talked about before, a normal or a bell curve, because the variable can take any value. The x-axis is the variable here, and the y-axis is usually the repetition, how much it happens. So each one of these values is going to be having a 0 repetitions. However, we're going to have some kind of range here instead of a specific value. So we can have also either normal, but it can also, depending on what variable you have, you can also have here what we call here exponential, or some kind of another distribution that's called chi-square. These are distributions that define here the continuous variables. The other distribution here you have a value that's in the middle for the normal. The exponential and chi-square may have different distribution. We have another you can say mean here, or not a mean, where a value where most of the observations come around, and then you have when you go up, you have less amount. So we have here different distributions, but most of our work here will be using normal distribution. And then we have here discrete when you count. That's easy it is. And the most easy one, we probably have heard this a lot in your statistics class, and probably you hate it, is that when you flip a coin, head or tail. So it's discrete, either or. There is nothing in between, either or. Or again, another example you might see a lot in your statistics class, when you hit a dice. You cannot have 1.5 in a dice. 1, 2, 3, 4, 5, 6. So this is called discrete. When I'm in class face to face, I want to know how many people are sleeping in my class, or how many people in a train. Well, you cannot have one person in a norm. You have to have a discrete. So we work on this kind of discrete. We have lots of discrete distribution or discrete statistics in our class, because we do lots of counts. For example, volume is discrete. Number of people in a toll station is discrete. We have different discrete values that we use in this class. How do we do it? We also use normal distribution in discrete. I'm going to show you how. But also the most famous discrete models are these here: Bernoulli, binomial, and Poisson distribution. So you might remember this from your statistics class. Don't worry, it's going to be much easier here. It's going to be much more practical. So let's go ahead and work on the different data. How do we organize data? And I know this example doesn't look very well. We usually get the data and we organize it in different ranges. So for example, I think this was data about different years and the baseball results, I guess. And it's the numbers between 60 and 80. So you can see here it's continuous because we have different decimal points. So what we did is that we start counting. So we take ranges from 60 to 62, 63 to 65, 65 to 68, 68 to 70, 70 to 74. So here we have ranges that should be equal. And we simply just go ahead and count how many observations. And we create this very, very famous statistical curve that we call here histogram. In class, I will do one example with you in creating a very easy histogram. Another example, this shows much better than the previous slide here. Yeah, this is the baseball example here. Number of leading runs. I'm not a big baseball fan, so I don't know exactly what does it mean, but you're going to tell me, guys. And you can see we can use it here for both discrete, or we can use it for continuous data. So here, when we have numbers over a 50-year period of this RBIs, all we have to do is just go ahead and count how many number of observations. So I'm gonna just do one of them very fast, so to move over, I don't want to make this video boring. So here we divided our data or this variable here into different categories. Each category is 10 points, 10 RBI points. So for example, from 100 to 110, all we have to do is simple counting. So here you go and count how many values is between 100 and 110. I have this one, 1, and I have 2, 3, 4, 5, and I mark it so I do not count it again. 4, 5. So we have here probably 5 repetitions, and I keep doing this. Once I do this, I go ahead and start drawing a curve. You can see here the curve that goes from for different values. So I create the ranges and then I count, and later on I'm going to learn how to now find out of this data what is your average, what is your mean. We talked in class about mean, median, mode, and also we're going to do something called standard deviation, which tells me how my histogram is distributed. Is it something like this? Or is it something like that? Or is it something like this? This is different curves that tell me how distributed my data is. Is it around your mean, or is it distributed really randomly, or a little bit more distributed around this mean? So now let's talk about the estimators. Estimators is all descriptive statistics. You all know about it. It's easy, you do it all the time, but we're just going to put it in some kind of statistical equations. So we talked about this in class on Friday, that the first statistical estimator is measures of central tendency. When we have data, we want to figure out what is the value, one single value in which this data goes around. And the best way to describe this is the arithmetic mean. Sometimes we call it the average. So the equation here, you probably know that. Or go ahead and add up all the values, divide by their number, and this gives us my x mean. Okay, let's get back to the equation, the example here. In case I have ranges, how do I do it? Well, we go to this equation. So this equation is so straightforward. How to do it? Your mean is equal to, let's say that you have different groups. Let me draw the curve here. Here, this is group, and that's a group. Remember the group in baseball, the first one was between 100 and 109 or 110. So here, this is the number of, I count how many observations, like I did remember when I had 5. So this is how I do it. I create a big parentheses, and I say here 5, that's F here, number of observations in the first group. And what's the middle value? 105. So it's 5 times 105. This is what we did in one of the examples before, which we call here the weighted mean. Then plus, and this is the plus here comes from this sigma. Sigma is the summation. So plus, and I do it for every single group. I add the repetitions of every category and the middle value of it, or the mean of that. And then I divide by the total number of observations. In my previous baseball example, there are 50, because it was in 50-year period here. So I do it for 50, so n here is equal to 50. So I add them up, and this is called the weighted mean, and I divide here by 50 in my previous example. So I do it for every group, and I get the weighted mean, or the group data. We use here the midpoint of every single group. So for us to calculate the mean, I'm going to do this in class. I'm going to use your calculators. I go ahead and I put these numbers here, add them up, and then divide by their values. Or if I'm going to do the grouping thing for bigger datas, I just count and find the mid value of each of them, and this is called grouping data. Grouping data when I have more data, but this is easy. We have here 1, 2, 3, 4, 5, 6, 7, 8. So we have here less than 10 values of mean, and you calculate the mean by just adding them up. So we did this for the previous example here, and I'm gonna do another example in class once I meet with you guys. The second measure of central tendency is the median and the mode. Median, we did this in class, if you remember this, when we arrange in ascending or descending order, it doesn't matter. So we have here 1, 2, 3, 4, 5, 6, 7. So when we have 7 values, we pick up the guy in the middle here. Well, after we arrange the numbers in a descending order or ascending order, and that will be my median. If I have an even value numbers, so let's say 8, 3, 4, 5, 6, 7, 8, I take the 2 mid values. So you can see here I have 3 up and 3 down, and I take the average of these 2, and this will be named the median. Also, we talked about the mode. The mode is the simplest one here. It's very practical when we have discrete data, when we have counts. The mode is the most repetitive number that you have. Also, this is the best when we have lots and lots of data. And now Excel and other statistical software helps a lot when we calculate these. So, this is the first thing, the measures of central tendency. And then we're going to measure something else when we have here your histogram. And your histogram is always being turned into this kind of curve. And we have 2 types of curve. This is one, and this is another one. The first one is a very to itself distribution, or data that's all they go around your mean. Another really good type of data is this one here. You can see here most of the repetitions is around the mean, meaning that the data is very similar. For example, if you're measuring speeds around the road and you want to figure out, are people driving on almost the same speeds, or do we have a big difference in speeds? And why do we do that? If you have a highway with people driving 20 and other people driving 80, expect some crashes because there's a difference in speed. So we want to measure here what we call here measures of dispersion, and the best measure of dispersion we use a lot in statistics, something called variance and standard deviation. Simply, your variance is square the standard deviation. So they're the same. One is just power the other, or power to the other. So let's calculate here the standard deviation. Standard deviation is equal to V is equal to S square. I'm going to tell you the difference between sigma square and S square. So easy. Again, guys, it's so straightforward and easy. So S square here is the difference between any value you have in your data minus your mean that you got in the previous step, and then you square them and then you add them up. That's why it's lots of work here, and again the computer can help us with that. So what does it mean? For our this example here, let's say that the mean was, just for the sake of example, was 40. So how you calculate your standard deviation? You say here 53 minus 40. Each one of these values and square it, plus 41 minus 40 and square, and so on. You go for each number and you subtract the mean and then square it, and then divide by what? You divide here by n minus 1. So in this case, the baseball example case, you use 49. If you want to find the standard deviation, you just go ahead and calculate the square root of your variance. So this is how you do it. This is another equation of how to do it in case you have ordered data in different groups. So it's sigma, the frequency of every group, times the mid value of every group, minus n, which is number of observations, 50 in the baseball case, times square of the mean. And you do this for every single group. So you have, let's say, 5 groups. Remember, we had, for example, I'm just going to for the first group. So you go ahead, I had 5 repetitions times 105 square minus 50, and let's say the average was 113 square. And I do it for every group, and then I again divide by n minus 1, which is 49. So I do plus and plus and plus. Once I'm done, that's the variance, and then I square root everything to calculate the standard deviation. So the standard deviation is a number that has the same units as your variable. So it's in feet if you're calculating heights, it's in speed, miles per hour if you're calculating speeds, and it gives you some kind of a variance. What is the spread? And we usually also put it in plus and minus, since this is square root. We put it in plus or minus. It could be more, it could be less. So when I say here the average speed in this road is 50 miles per hour with a standard deviation of plus or minus 5, then your spread, this is the average value, you're going here plus or going minus. See guys how simple it is, statistics, and how can we use it in our traffic engineering class, and using it for data as well. Another measure of the dispersion here is something that we did in our previous lesson or previous lecture when we talked about the percentiles. The percentile also gives me information. Remember when you talked about the TR, the reaction time, that's another random variable. When I said, for example, 85% of the people have 2.5 or less, this also gave me an idea. Do we have a huge range of people that have different values of TR or speeds, or most of the people have the same characteristics or almost the same. So here we have usually this 85 and 15, and not surprisingly that the 15 percentile is one of the measures of your central tendency. And I want to ask you a question, guys. Out of the three values that we calculated, which one is the 50th percentile? Is it the mean, the median, or the mode? I'm going to ask you this question here, guys, and I want you to answer the question on Friday once we meet in our classroom. And sometimes you can calculate the standard deviation by estimating its half, the difference between the P85 and P15. The P85 is the percentile. So let's say here, when I have, for example, the TR, the 85 percentile was 2.5, and the 15 percentile was 1. But let's say 1.5, just to make it easy to calculate. Then for you to get the estimated standard deviation, well, you can easily know now what is the 50th percentile. So the 50th percentile is 2. It's just the mid value here. And the estimated standard deviation is, go ahead, 2.5 minus 1.5. So that's 1 divided by 2, so it's 0.5 plus or minus 0.5 seconds of reaction time. So when I want to represent the data, I say, you know what, this data, we have an average of 2 seconds of reaction time, and we have plus or minus 0.5 error. We can put it as error, or people are spread around 2. We have people who have faster reaction time, around 1.5, and we divide this by 2. Any questions, guys? Well, I'm gonna get any questions in class, because I'm gonna end here before we start the normal distribution. I'm gonna put it in another video. So have a great time, guys, and see you in the next video when we talk about the normal distribution.